Hello to viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about habitable planets. So let's dive right into it. Well, first, you have to understand what the heck we are talking about. We are talking about anything that is outside of our solar system. In last episode of Future Friday, we talked about exoplanets. This is basically a subcategory of exoplanet. Basically, we are talking something that is outside of Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Pluto is not included. So basically anything that is outside of our solar system and yet can show signatures of that it I am truly sorry about that. Can show the signature that it can harbor life. We will classify that as habitable planet. Now you have to be mindful because we do not have warp technology or faster than light travel. We cannot just go there and double check it, so to say. While in terms of other things, like let's say what is the mass of the planet or like what is the star signature, we can be damn sure if we are saying that like okay, there is a planet there in this star system. We can be damn sure when we actually go there, it will be there. It's absolute. It's very crystal clear. We cannot be like confused right now. But when it comes to habitability, we are still looking at signature, so to say. Nor we have the tools, nor we have the experience to be like, okay, this is what we saw, this is how we went there, this is what was the deviation in the data, and this is how we calibrated it. We are not there yet. All we are doing is basically looking for science. Now, one thing you have to understand, in science generally it is recommended to analyze multiple things. Basically, if you want to understand rock formation, nobody would say just look at like iron oxide. People will say look into everything, look in how sodium reacts, look in how basically whole of the periodic table reacts. So you can get a much thorough idea. Basically, you can build a much better foundation. So we are trying to understand habitability. Habitability of what? Basically life. So we have to understand life. Here's our problem. We only know of one place which harbors life. That's the biggest problem. Like in science generally you do not want to do this. Let's say for example in celestial bodies, if you want to understand moons, our solar system is bombarded with moons. We got more moons than we can count. Basically we got moons which has an atmosphere. We got a moon which is very hot and volcanic. We have moons that are very radioactive. Like we got all like we like moon wise, like which moon do you want, like what size of moons do you want? We got them all, so you don't have to worry about moons. We have a lot of test study to study from, but in case of life we don't. So that creates a problem for us. Like scientifically it's a problem because how we see life is directly affected by one fact that we have only one source of data. So everything we are looking outside or every thought we are projecting outside is based on that one data point, life on earth. So that what does that translate to? What happens? Basically our search for that habitable zone becomes a search for water. Why? Because water is the core of life on earth. Why is that? Because water is what we classify as universal solvent. So basically it can mix everything. So if you want to create a life, basically life is a chemical engine. Chemical engines are inherently a chemistry level device, which means you have multiple molecules interacting with each other. That can only happen properly in a liquid. It's not impossible to happen on a solid, but the probability is like very low. So if you want to create something complex as like life, water is generally preferred. Now another aspect of water is also very interesting. Water is very stable for a very long temperature range. It's not like okay, it's a liquid only in lower temperatures and then it evaporates. It has like freaking 100 degrees Celsius range, basically from 0 to 100 degrees Celsius. Now again, if you want to make a complex chemistry, it will not be stable if at 100 degrees Celsius. Very few chemical bonds, if they are very rigid, only then they can survive at 100 degrees Celsius. So still from a practical standpoint, you still get a lot of temperature range. You can be like hey, from let's say 10 degrees Celsius to around 40 degrees Celsius, you can easily have a life forms. And we have on this planet itself have life forms that have survived at much hotter waters. So we know for a fact water is the key to life. Now what is the key to water? Temperature is the key to water. So this is what we are looking for. We know for a planet fact that there is a star. Okay, we got that. What else? Star has a radiation energy. Basically it's radiating energy. Now if you are too close to it, you will get toasted. Done. Simple. There is no extra calculation there. What if you are too far? Again, you will freeze to death. No matter what kind of greenhouse effect you have, if you are too far, it will simply not work. Flat out. So we know for an absolute fact there is a too cold, there is a too hot. So there is a zone in between. Now that zone is what we call basically Goldilocks zone, habitable zone. Pick your name. Basically it doesn't matter. Basically there is a green zone where our mathematics suggests that there is a planet, and if that planet is inside that zone, there is a very good chance it can support, be mindful of this word, support liquid water. We cannot guarantee, because if you take our own solar system, it's like okay, take the solar system and apply the same mathematics, you will find Mercury is not there. Okay, awesome. Venus is there. Earth is there, absolutely. Mars is also there. So we have three planets, and only one of them is habitable. So things like that happen. So it's not a absolute thing. Be mindful of that, because we have only one data point of life, and we start to start and end our thoughts of life form regarding water. We have to start this as a first ruling things out. If it's too close, we are not even gonna bother looking. If it's too far, we're not gonna bother. Basically, it's like a filtering process. We are filtering things out. You have to be in a habitable zone, at least initially, for us to take you seriously. So that's our zone. This is like first clue. If this clue does not, again, it's not a guaranteed thing, because we cannot go there and actually double check it. It's just a rough guess. Like, this is the first filter we apply. Is it in a habitable zone? Can it support liquid water at its surface? Then we come to the another aspect. Atmosphere is key here, because why all three planets, basically Mercury, Venus, Earth, and Mars, why the heck they all three are different? Because of the atmosphere. Because Venus and Earth, both of them could be absolutely equal to each other, like in every single way. Venus can sustain its atmosphere so close to Sun. Why? Because it has strong gravity. Its gravity is almost equal to Earth's gravity. That is why it has such a thick atmosphere. Its atmosphere is like more denser than Earth's atmosphere. So flat out, we know for a fact that Venus can be made like Earth. It's the only planet that we know how to terraform. But Mars cannot be made hot. Why? It simply does not have an atmosphere, nor it has a surface area. And so even if its atmosphere is 100% carbon dioxide, it still does not trap enough heat. Why? Because Earth's atmospheric pressure is around 15 psi, while Mars atmospheric pressure is around 0 point some psi. So flat out, for this matter, we understand the importance of basically atmosphere, and that's the reason why we worried about basically runaway greenhouse effect, because we know what happened to Venus. So atmosphere is very key. Now atmosphere has a signature. That's the one good thing about it. So whenever a star sends light to us, that light has encoded a lot of message into this. Now this message, if you know how to decipher it, you can figure out the composition of the star and signature of that. So you will like, this star has this black bands at this point. Again, there are people whose sole job it is to study it and understand it, and they can be like, yeah, this is how it's gonna work. And they can tell you. Now here's the interesting thing. You got a star's default signature. I'm looking at the star, this is what I'm getting. But what happens when a planet moves in front of it? Lot of light bleeds through. Now during that bleed through, they will go through the basically planet's atmosphere. Now here's the interesting part. You know a default signature, but something tampers with it, and then it goes back to the normal, because again, planets are not static. They will come and they will go. Now you have two data points. Utilizing these two data points, and you will compensate for it, you will figure out what is the signature of that planet's atmosphere. Now you know for a fact what is in that damn planet's atmosphere, hundreds of light years away. And that's what would be the one of the unique selling point of the spectral graph that is put into James Webb telescope, because it can precisely tell what is in other planets' atmosphere. So basically, if Earth was spotted somewhere away, they could easily say, hey, this has a nitrogen and this has oxygen, with definite certainty. Other gaseous mixture would be a bit difficult to spot, but nitrogen and oxygen, we got it. Same. That is why spectrographs are so important, and we can easily see it during transit. However, that's the consequence of it, because while gravitational method does allow us to see planets who are not aligned to us, this will only work if it's perfectly aligned. So basically, star, we as an observer, and the transit has to happen in front of us. If it's happening like this, basically it's not cutting the light of the star, it will not work. So there is a certain limitation of that, but it does work. And so far we have more than enough planet to in a transit catalog, so we know for a fact that we can find at least some that meets our need. Now another aspect you have to think, because of the hype media that we are in, every Tom, Dick and Harry is like takes it and like stretches it. It's like Earth's twin. Dude, no, just no. There are way too many unknowns. Ask any planet scientist. They're like, dude, there are like we barely know two things, and we know 300 things that we should know in order to classify it, and we don't know any of them. So there are a lot of unknowns, and there are many things that you flat out can't see from this far away, because the nearest planet that we can mathematically think about is 4 light years away. Yeah, that's not a distance where you can be like, okay, I'm gonna take a picture. No, that's not happening. So there could be many things. For example, radiation could be a very serious thing. You could see a planet. Heck, you may even send a human mission to it. Again, assuming you have warp drive. Let's say you do that, and then when they actually reach there, it's like, bro, it is way too radioactive. Again, things like that can happen easily, and you will not be able to spot it from multi light years away. Then we talk about wind speed. Let's say you found a planet. Everything is awesome, but here's the deal: Earth has a very stable atmosphere. That's not guaranteed. You can have an atmosphere that is stable chemically, but physically it's very unstable. It could have tornado 24/7. Like, let's say for example, Jupiter has storms that goes on for thousands of years. Good luck trying to terraform there or actually settle there. So there are many subtle things that we do not think about, and because of our distance, we cannot know about this with any certainty. And what about tectonic stability? Maybe you find a planet that's like, whoa, everything is like damn, everything is awesome. Here's the deal. The reason why it's everything is stable, because there is a period of tectonic shifting. Things of that nature could happen, and you would are just seeing something like there was a lot of life there. That's why the oxygen is there in the atmosphere, but a giant tectonic event eroded everything away. So things of that nature could happen. You can have many unknown scenarios, like you built a settlement and lava is just like tada. So there are far more unknowns than there are knowns. We can only tell us with some certainty there should be water on this surface based on the atmosphere. And if we can see the atmosphere, these two are the only clues that we can be bit sure. We're like, okay, this is what we know. So right now we are not in a position where we call Earth's twin sister has been detected. Yeah, that's just like stretching it, because technically speaking, that same logic will tell us Venus is Earth's sister. I'm pretty sure you should not compare Eden to hell. So what is our hope? Basically, at this point in time, same way we went from in exoplanet hunting to like maybe someday something to like, oh, whoa, hundreds of exoplanet. So same, we have to do this here. Basically, we have to take our exoplanet hunting gears and multiply them. Basically, imagine hundreds of tests, something like that. And then we have to make better tools like James Webb telescope. Now, this telescope is a bad telescope simply because again, it costed way too much. It has like tangibly, like people are showing like, okay, this mission has been cancelled because of this mission has been cancelled because of like it has more cancelled mission than successful mission. And god helps everyone, like if it blows up in the launch pad, there is no 2.0 of this. So again, but it still is a better tool. So not only we need more tools, we need better tools. So once this puppy will be the first layer. This will sort out like junk from basically clean products. Once we know the clean product, then this puppy will actually use their high quality spectrograph to analyze it thoroughly and properly. So we need much more tools. Basically, this is a completely new field that you are seeing becoming something real in front of our eyes. This is a new field of study that is taking shape right in front of us. That's the amazing part of it. We are seeing new science being built. So this was my presentation on habitable exoplanet. I hope you learned something from this and liked it. In that scenario, please click like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me excess disappointment, and please leave a comment because I like to reply to all of them. And subscribe, press the bell icon if you're free. And as always, thanks for watching.